I'd like to talk a little bit about watersheds and how we delineate them in a GIS. Now, a watershed is a pretty simple concept. It's an area that captures flow, so it contributes to the downslope flow to a point in the landscape. So you can pick any point in the landscape and look at the uphill watershed. Typically, we're interested in watersheds that drain to a stream or some water course. So we want to know all the area that's gathered above a particular point on a river or stream someplace. And the drainage network then is where the water is at the surface. It's in a raster environment, the set of cells on which water is flowing. Now, there are various methods in GIS to estimate what these are. I have to say that they're usually wrong in some level. It's hard to use GIS and terrain tools, so data for elevation, and get the water courses exactly right everywhere, especially up at the ends where the water is first starting to form into streams. So you can estimate or approximate where they are, but the best way to know where the water courses are is to walk them and digitize them. Unfortunately, that's dreadfully expensive and sometimes hard and dangerous. Like, could you imagine trying to identify where the water courses go up here in this mountain environment? Although it might be fun, it'd be hard to do. So remember that these outputs should be taken with a grain of salt and really should be verified on the ground if you want the utmost accuracy, but that's kind of true all the time. Remember then that we're using a raster data layer to identify our elevation, and then we use those differences in elevation to get the direction that water might flow were it to be put on the surface. So you get this flow direction. It doesn't have to be from cell center to cell center. In real life, it often isn't. Also remember that we can have both divergent and convergent areas within a cell. So I've overlain here the boundaries of some imaginary cells on a 3D kind of rendering, a shaded relief rendering. And you can see that within this cell, if this were the approximation we were using, we would have flow, real flow in two directions, that's divergent flow, or convergent flow into the cell, as opposed to sort of a uniform cell where water is flowing only in one direction in the cell. This is usually the case. We typically control this by making our cells so small that divergent or convergent flow isn't that important to us, that it's at a small enough grain that it's just churn within the cell and we don't care about it. But again, that's not always the case, and you have to think about it. So watershed delineation is a multi-step process, so we typically have to condition the DEM. We have to make sure they're in the same horizontal and vertical units, and they cover our region of interest. Now, this is not always the case. Often when you project data, you change the horizontal units, but you often don't mess with the vertical units. So you could reproject from a UTM to a state plane coordinate system, and you switch to a feet-based horizontal unit, but the vertical units might be in meters, and so slopes you calculate would be wrong, and that's not good. You have to fill the DEM, and this is appropriate in a lot of landscapes. It's inappropriate in others. You have to be careful how and when you apply this. But basically, you're getting rid of artifacts in the data that keep water from flowing. Basically, you're looking at downhill direction. If you have a small layer that raises one point above another in a fairly flat area, the water won't flow past it, even though it should and does on the landscape. Then you calculate flow direction, flow accumulation, some threshold for stream definition. You can define outlets, and from those outlets you get watersheds. So here we have a target landscape that looks something like this. We have these two main draws and 2 points we want to calculate the watershed for, what drains to these 2 points. Now we have to fill our data first, and we do that because there can be these sinks, local areas where water drains in and doesn't come out. So here we show in white, and this is from the GIS Fundamentals textbook, areas that wouldn't drain, areas where we have a fairly flat stream, fairly flat topography of the stream running through it. And if you had a little bit of error here in collecting the data, this cell is higher than the ones that drain above it, and so it blocks or effectively dams the water from coming out. Unless I either shave that cell down or fill above that cell, this area is not going to drain. So things will drain into it, but they never come out because it's uphill all the way. You can often see fills or areas that need to be filled by looking at a profile. So here is an actual data line that was generated from one process, and then here's some elevation data below it. So this is the putative stream course. And when I look at a profile along that stream, so I look here, starting at the base and going up along that stream, I see that, yeah, as I go horizontally, it's always downhill to the next cell. So here's the horizontal and here's the vertical dimension. So water is going to flow downhill. But if I look along this other course, the red one here, I'll see that there's actually a bump. Right, so the water goes up and comes down, and then I go uphill. So if I'm flowing downhill, I come into an area that's a catch area. Now, if I know that's not the case, if I know that this is in fact a connected stream, my DEM isn't representing this cut through here, and so I'll have to do something to fix that DEM. If I don't, when I look at above this point, the watershed, I get a watershed coming up in this direction that's more or less correct, but this one, see, I'm cutting off the top because that bump keeps things from draining down through it, so no flow comes into it. So I get a goofy watershed here that's off instead of getting the whole big one that I want. Again, you can see this in example in the book where I used an unfilled and a filled DEM, and you can see that basically there are places here where there are breaks in the streams. So the water will come down and then it comes to one of these bumps and it doesn't get past that. That's a sink. And so the water doesn't drain past it. It drains into a sinkhole. Same thing here. So we're getting these little areas that are odd and outside the watershed. Now you have to be careful, I said, when filling, because here we filled and have the correct watershed because I know this is a topography where this drains. In some areas, in karst regions in southeastern Minnesota or in Kentucky, parts of Tennessee, lots of other places, there are local drains where water drains in and doesn't come out, local low spots, and I wouldn't want to fill those inadvertently. So you have to know the geology and not apply these wrongly. Here I can look at the fills, or the sinks here, the areas that needed to be filled along my water course through a sink identification routine that we'll cover in labs. And you'll see here that these are places where there are local high points and water doesn't drain past them. So I have to fill these cells. It might be where there was a log across the river when the LiDAR data was collected to get the elevation, and so it looks like it's higher than it truly is. And so I want to avoid those and make sure that I get the proper flow directions. Another thing about these flow directions is there are various ways to represent the flow direction. So once I've filled the cells that needs to be filled, the sink cells, I need to calculate the flow directions. And you can see that they often go between the edges, between different cells. So it looks like it should point at multiple cells. And there's a couple of different ways to represent them. The most common way is this called a D8 flow direction. And so if the direction is anywhere along the edge closest to the cell, then it's going to give all the flow to that cell. So it basically says every pi here that's in each of these cardinal and subcardinal directions, I'm going to give all the flow direction to the adjacent cell. So if it's between basically the middle half of this line, all of it goes to this cell. If it's between this part, so I look here at the plus or minus 22.5 degrees off the line going between these, all of it goes to this cell. If it's in this middle region here, all of it goes to this cell. So there's only 8 flow directions. They're discrete, and all the flow goes to one of those cells. Now this can lead to some interesting configurations of watersheds across the landscape. You can, especially in flat areas, you can get big errors in the watersheds. It's often adopted because it's easy to code and it's easy to calculate the various flow accumulation or other layers off of a D8. It's much more difficult off of these multi-cell methods. So the simplest one is this D-infinity method, and it proportionally assigns the flow to one downhill direction. So it calculates the steepest downhill direction, and then it just assigns a flow proportional to the angle between these two cells. So if the angle is pretty small, it gets a proportionally large amount of the flow. If the angle is big, it gets a proportionally small. So cell 2 would get more of the flow than cell 1 in this instance. These are generally better. They generally lead to more accurate estimates of watersheds and flow accumulation and flow direction, but they're often not coded. So once we calculate a flow direction, we can plot this, and this is the D8, and so it's coded, 1, 2, 4, 8, 16, 32, 64, 128. I don't know why they chose this, but that's the way they did for these various cardinal and subcardinal directions. You can see by the color which directions they flow, and you get patches that are all acting in the same direction. And so you get something that looks kind of like this. The flow direction arrows point away from the ridge lines and towards the streams, and at the streams they have flow directions only pointing into them. So we get this flow direction. We can then get flow accumulation, and flow accumulation basically says, look, I'm going to start at the bottom or at the top, and I'm going to count how many flow into a cell. So this cell, what flows into it? So this cell flows into this cell. Then I'd say, okay, this cell, what flows into it? Well, these two cells do, and maybe some other cell. I don't see any here. And this cell, well, what cells flow into them? Well, this cell and this cell flow into it, but then these cells flow into that. So I can count going down how many cells flow into each of these, and the number increases as you go downstream. The ones near the ridge would just have one cell. The ones in the stream would have lots and lots of cells, and when you get down to the bottom of the stream, all the cells for the watershed point to it. So this is basically assigning the flow accumulation, the number of cells or the area, and it increases as a function of the area that drains in. So you need this flow direction, and then you can calculate the flow accumulation. And if you calculate the flow accumulation and you give it a regular stretch, you get something that looks like this. You get these little dendritic patterns coming out, and they get grayer as you get fewer and fewer cells till some threshold where it's black, there's no color. And you can then assume these are going to be the water courses, because that's where everything's flowing down into it. Now, if you have unfilled sinks, you'll get breaks in these. It'll be getting brighter and brighter, then you get a break and it goes black again, and then it starts to get brighter and brighter as more cells drain into it. You can then apply a threshold and say, okay, how many cells constitute a stream? If I have 100 cells, 500 cells, 5 hectares worth of cells, and then you threshold them, and everything gets a 0 that doesn't have up to that number, that doesn't have more than that number, and then everything more than that number gets a 1. And so that's the stream network. You can stream threshold. So again, we would figure out what the number is, look at the cells that have that number and give them a value of 1 beyond that. We can then look at the flow direction and get the watershed. So we can pick from a point and say, okay, I'm going to move upstream opposite to the flow direction until I get to these cells that have a value of 1 at the edge. And so I just basically walk upstream, and that's what happens in these from a given point, an outlet point. You walk upstream and delineate the watershed. So you first have to set an outlet, and then above that, it walks up until you get to all these edge cells that have a value of 1, and then stops looking above it, or whatever the area is if you're counting area. And so that's how you'll delineate then the watersheds. You get a watershed area, and then you can get a watershed polygon from that.